I'm going to describe our Eiger system that provides stronger semantics, that is, more powerful tools for low-latency geo-replicated storage. So what do I mean? What do I mean when I say geo-replicated storage? I mean the back end of massive websites, things like Facebook, Reddit, and Amazon. And I mean the storage that holds the data for that service. So this includes things on Facebook like your profile, who you are friends with, what you like, your status updates, and so on. From a distributed systems point of view, there's two interesting dimensions to this storage. One interesting dimension is the many-node dimension. We have this massive amount of data. It's far too large to fit on a single machine, so instead we need to spread it out across many machines. The way that we can do this is by sharding the data or putting subsets of the data on different machines. So for a social network, we could do this by last name, and we could put Ada Lovelace's data on the server for L and Alan Turing's data on the server for T. Our other interesting dimension is the multiple data center dimension. So we're replicating data from one location to multiple other locations. And there's a couple of reasons for this. One is fault tolerance. If one of our data centers goes down, we want our service to remain available and people to be able to use it. Another reason is to get data close to users. We want our service to be fast, so we don't want users to have to go far away to get to that data. So now that I have this sharded and geo-replicated storage system, how do I actually build a web service on top of this? Well, in each one of my data centers, in front of the storage replica, I have a tier of web front-end machines. And when clients connect to our service, they're connecting to one of these front-end web tier machines. And then that machine is going to read and write data from our storage tier to interact with the service and to build the client's pages. At a high level, we have two conflicting goals for our storage system. One goal is low latency. We want things to be very fast. We want them to be fast because this gives users a more responsive experience, and because many studies have been done and shown that there's this correlation between page load time, user engagement, and revenue. So we want things to be really fast. But we also want things to make sense. We want strong consistency so that operations appear in an order that makes sense to users and is easier for programmers to use. But unfortunately, these two properties are fundamentally in conflict. Specifically, theoretical results say that low latency and a consistency model that includes a total order over operations are fundamentally incompatible. So this means if we want low latency, we can't have things like linearizability, serializability, or sequential consistency. If we look at the space of systems, some are on the one side, strongly consistent systems, and some are on the other, low latency systems. So a strongly consistent system is Megastore from Google, originally presented at SIGMOD in 2008, which is a strongly consistent wide area system that has quite a few wide area round trips in it. On the other side, we have things like Dynamo from Amazon, presented in SOSP in 2007, which is a low latency system, but which settled for eventual consistency, which doesn't really give you any consistency. So recently, there have been a number of research efforts on both sides of this divide, pushing on what each side can provide. On the strongly consistent side, we have systems like Spanner and Gemini from the last OSDI and Walter from the last SOSP that tries to make strongly consistent storage more efficient by minimizing the number of wide area round trip times or optimizing for the common case. On the low latency side, we have our previous work on the COP system from the last SOSP that started to push on what we could provide for guaranteed low latency storage. And our Eiger system is also on this side of the divide, and we're continuing to push on what we can provide for low latency storage. At the end of the talk, I'll specifically detail the differences between our Eiger system and our previous COP system. So what Eiger does, while guaranteeing low latency, it tries to obey user expectations, and it tries to make it easier for programmers to use. In particular, we're going to provide causal consistency. So operations appear in an order that makes sense to users and programmers. A rich data model, so you can build a web service on top of this. Read-only transactions, so I can consistently read data that's spread across many nodes in my system. And then write-only transactions, so I can atomically update data spread across many nodes. So how does our system ensure low latency? It's by keeping all operations local inside our local data center. So when a front-end web server sends read and write requests, these are served entirely inside that data center. And we're never going to block them, and we're never going to require them to acquire locks, so they can always return right away. And this is how we ensure low latency. Now, in addition to being fast, we also want things to make sense, so we provide causal consistency. So causal consistency says this: if operation A happens before operation B, everyone will see A before they'll see B. So this is great for users because now their web services behave in the way that they expect. Let's say I remove my boss from my friends list and then I post that I won a new job. In an eventually consistent system, people can see these operations out of order. My boss could see my update. In a causally consistent system, that's never going to happen. Or on Amazon, let's say someone adds something to their cart and then clicks on their cart. In an eventually consistent system, they might not see what they just added. In a causally consistent system, they always will. Causal consistency is also great for programmers. So think about someone at Facebook that adds something to their timeline, they like something, and then they decide, I want to hide this. In an eventually consistent system, I can get this hide operation before I get the thing that I'm trying to hide. In a causally consistent system, I'll always get these two operations in that correct order. So in our comp system, we provided causal consistency for the key value data model. And so this is great as an opaque cache, but it's not the right abstraction to build a full web service on top of. So one of our contributions in this work is bringing causal consistency to the column family data model. So this was introduced by Google's Big Table system, and it's also used in the Cassandra system from Facebook and now Apache. So we overcame quite a few challenges in bringing causal consistency to the column family data model. This includes, how do you handle operations that update and read many columns at a time? How do you handle range queries over columns that are concurrent with deletes to those columns? How do you handle counter columns that are commutatively updated instead of overwritten like a normal data location? So I don't have time to go over those details, but I encourage you to check out our paper or talk to me this evening at the poster session to find out about that. So even if we have a consistently updated sharded geo-replicated storage system, it's still not easy for a programmer to extract a consistent view of data in that system. And the reason for this is because we're sending asynchronous requests to distributed data. So here's what this looks like. We have a local data center, and in that data center we have a server, and that server is accessing its local replica of the data store. So this is where the data is spread out across many machines. We have A on the first machine, B on the second, and so on. And the server is going to send out concurrent read requests for A, B, and C. Because it's an asynchronous network, these requests arrive at different times. So we're going to get back the data for A right away, but we haven't gotten it back for B and C yet. Now concurrently, someone else updates the data. So we have updates to A, and then B, and then C, and now my read requests arrive for B and C. Now back at the client, I have some data from before these updates and some data from after these updates. And I don't actually know what's going on, even though my data store itself was always consistent. So what we want here is read-only transactions. We want a way to consistently extract data that's spread across these many servers. So in our system, we have logical time flowing around. We have Lamport clocks on all of our nodes and carried with all of our messages. And this logical time gives us a global view of the data store that's fully distributed across these servers. So this is what it looks like. So here we have some data locations, A, B, and C. And for each data location, we have a value that's written at a certain time. So each location is moving forward in logical time. And our insight was that this store is consistent at all logical times. So if we want to return a consistent view of the data, we simply need to return data that was all valid at one particular logical time. This is exactly what our read-only transactions do. They're going to extract a consistent and up-to-date view of the data from one particular logical time that's spread across many servers. Now, in designing these read-only transactions, we overcame a number of challenges. These included, how do we ensure scalability? So our data is spread across many nodes in the system, and we want to be able to continue to grow the number of nodes. So how can we ensure that? We do that with a fully decentralized algorithm. Another challenge is guaranteeing low latency. So we're on the low latency side of that fundamental divide. So we want to make sure that we stay over there. And so we guarantee low latency with an algorithm that's going to take, at most, 2 parallel rounds of reads in the local data center, and that never blocks and never acquires locks. And then finally, we wanted to ensure high performance. So our tagline for this line of work is don't settle for eventual. So we want to ensure that our performance is competitive with less consistent systems. And we achieve that with an algorithm that's going to take only one round of reads in the normal case. So our read-only transactions are extracting a consistent view of the data that's in this distributed storage and moving it onto the client. And here's how this works. We're going to start with a first round of optimistic parallel reads. So we're going to ask the servers, what's your current value for the data whenever this request arrives? And the servers are going to return that along with some validity interval metadata that says when in logical time was this value valid. We'll then inspect that metadata and choose a single effective time for this transaction. This is a logical time when the transaction takes place. Now, if there are not concurrent writes to the data that we're reading, all of our values from the first round will be valid at this effective time, and we can return right away. If they're not, and if there are concurrent writes, we might have to do a second round of reads to find out what is the value for this data at this particular logical time. To do that, we'll send out a second round of parallel read-at-time operations. So these ask the server, what is the value that you had that was valid at this one particular logical time that we chose? The servers return that value, and we can return right away, and at most 2 rounds of these parallel operations. So what is the intuition for our transaction algorithms? So our read-only transactions are going to read from a single logical time. So they're getting this consistent view from this single logical time. Well, we also have write-only transactions. These transactions allow you to atomically update data that's spread across many servers in the system. And this is going to be atomic in each individual data center, and then propagate out in the correct causal order to your other data centers, and then appear there atomically as well. So this is what that looks like. So write-only transactions appear at a single logical time. So either a read-only transaction sees everything from a write-only transaction, or none of it. And this is how we get atomicity for the write-only transactions. And as a bonus, these algorithms, as described, work for linearizable systems. So traditionally, in a linearizable system, you have these operations that are reading and writing values for a single data location. But with our algorithms now, you can consistently read or write data that's spread across many servers in many locations. So our Eiger system provides low latency so that things will always be fast, a rich data model so I can build web services on top of this, causal consistency so that operations appear in an order that makes sense to users and programmers, read-only transactions so I can consistently view data spread across many servers in the system, write-only transactions so I can atomically update data spread across many servers in the system. But what does all of this cost, and how well does the system scale? Well, to find out, we built a prototype of Eiger. So we forked the open source Cassandra system. We added about 5,000 lines of Java to that Cassandra system. And then we made this code available online. When we were evaluating our system, we wanted to answer those 2 key questions. What is the cost of our stronger properties, of our stronger causal consistency, and our stronger semantics with those limited transactions, versus an eventually consistent and non-transactional Cassandra system? So I'll show you the overhead for a real workload shared with us from Facebook. And in the paper, we also explore what's the overhead for a large state space of different possible workloads. And then I'll show you how well our system scales. So our big contribution is being able to provide these properties in systems where the data is spread across many nodes. So I want to empirically show you that our system can scale to large clusters. So here's our experimental setup. We have one data center. And in that data center, in this local data center, we have n server machines, where n is going to be 8 for the Facebook experiment, and then much more for the scaling experiment that we've spread our data across. We also have n client machines, each running many threads of execution that are fully loading the servers in their local cluster. And then we're going to replicate data out to a remote cluster, also with n servers in it. OK, so here are the results for that Facebook workload. On the y-axis here, I have throughput in hundreds of thousands of columns per second. So those are individual data locations in that big table that I showed you earlier, in that column family data model. The Cassandra system achieves about 500,000 columns per second in throughput. And our Eiger system is very close. In fact, the difference here is about 6.5%. So this is a really low overhead for the much stronger properties that we're providing with causal consistency and those stronger semantics. Now here's the graph that I'm really excited about. This is the graph that shows that our system scales. So these are the results for that Facebook workload. And along the x-axis, I'm going to continue to double the number of servers that I have in each cluster. And on the y-axis, I have throughput that's normalized to a single server cluster. So I'm going to take the throughput of the cluster and divide it by one server cluster. And hopefully we'll double that each time as we double the number of servers as well. So on the extreme side of this graph, where I have 128 servers in a cluster, I just want to point out this is actually a very large experiment for academics at least. So here I have 2 clusters of 128 servers and 1 cluster of 128 clients. So what happens is I double the number of servers in my cluster. We'll see that my throughput approximately doubles each time. We see near linear scaling. So the takeaway is that my system scales out, and I can continue to add capacity and throughput to my system simply by adding more machines to that storage tier. Now, we started this line of work with improving low latency storage with our previous COP system, and now we've continued it with Eiger. We've pushed on what we can provide while still guaranteeing low latency. So I want to detail some of our new contributions in the Eiger system compared to that previous COP system. So one new contribution is the data model. So in the COP system, we had a key value store data model, which was great as an opaque cache, but is not appropriate as a primary data store for a web service. So in Eiger, we provide causal consistency for this rich data model. Another contribution is providing a new read-only transaction algorithm. So our old read-only transaction algorithm in COPS was useful for causally consistent data stores, but wasn't applicable to all different types of data stores. The new read-only transaction algorithm you can use for data stores that have any type of consistency, including linearizability. We also have write-only transactions that are entirely new in our Eiger system. Performance is also better in the new system. So there were certain types of workloads that were somewhat unrealistic, for which COPS did not perform well. There are no workloads that Eiger does not perform well for. And then finally, one of the drawbacks of our COP system was that if you had a long-running data center failure, you would see that throughput would degrade. We don't have this limitation in our Eiger system. So in conclusion, our Eiger system is a low-latency geo-replicated storage system that provides the back-end for massive websites, things like Facebook, Reddit, or Amazon. We provide causal consistency for the column family data model so that operations appear in an order that makes sense to users and programmers. We provide read-only transactions so that you can consistently read data that's spread across many servers in the system, and write-only transactions so you can atomically update data that's spread across many servers. And then we demonstrated this in a working system. We showed it was competitive with an eventually consistent and non-transactional baseline, that we can scale to large clusters, and we released the code. Thanks.
Hi, Sanjay from Purdue. My question pertains to how expressive transaction support is in Eiger, right? So you've provided support for 2 types of transactions.
Right.
In practice, if you look at applications, how often is it the case that they do want these 2 types of transactions and none other?
Yeah, so we provide the type of transactions that we do because we can do those while still guaranteeing low latency. Certainly there's types of transactions that are more general that you'd like. Like if I was transferring money between 2 bank accounts, I would want to read something and then write 2 different things. And so this wouldn't be appropriate for that. But it's great for atomically updating relationships. So like in a social network, if I want to keep relationships symmetric, I can do one of these write-only transactions. Or if I want to read anything and just read it in a consistent way, then I'd use these read-only transactions.
Yeah, but I'm wondering, in what, maybe it's difficult to answer this, but do you have a sense of in what percentage of applications they might benefit from these but may not require other types of?
Yeah, so the types of applications that we are targeting didn't have any transactions before. So it's not like we're making a subset of previously usable transactions unusable. We're enabling new transactions for systems that need low latency.
Okay, thank you.
Hi, Marcos Aguilera from Microsoft Research Silicon Valley. So given that you provide read-only transactions and write-only transactions, it seems to me to be a fairly small step to provide general transactions in particular. Snapshot isolation you can think of as being a read-only transaction followed by a write-only transaction, and you have to do some conflict checking to see if there are write-write conflicts. But I think if you're just going to run two-phase commit in any case to provide the write-only transactions. You could do the write-writes, conflict checking, and get general transactions almost for free, right?
So that's the technique that you guys used in your Walter system. And the difference that we have is that we're guaranteeing low latency. So all of our transactions happen in one data center. We're never doing anything in the wide area. So we're never messing with write transactions. And this is one of the reasons why we have these limited forms of transactions instead of those general transactions. Because we never want to do anything in the wide area. We want to be able to ensure that we're always going to have low latency.
Oh, I'm sorry. I'm saying you can get general transactions almost for free, but you're saying that's not the case? You're saying that would be really expensive for you guys?
Yeah, so I don't think you can get general transactions almost for free if you want to guarantee low latency. I don't know what free is, but if you want to guarantee low latency, general transactions are not the right fit.
Okay, I guess we have to talk a little bit further on this.
Yeah, we should.
Hi, Rajesh Nishtala from Facebook. Can you comment about what the performance and the low latency guarantees would look like if you had a row or a column that had many write operations, like a lot of concurrent writes for, let's say, a popular object, and then a lot of other simultaneous reads to the system? Does it change the properties?
That should be fine.
Okay. Okay, let's chat after.
Nikita Borisov, University of Illinois. I think I'm missing something. So you mentioned that read transactions don't have to wait, but if you're doing the second read at time transaction, don't you have to wait till that node catches up to that logical time in some cases?
Yeah, so the way that the logical time works, the effective time for read-only transaction, when the message that says, can you give me the value at this particular effective time, when that arrives at a server, it will advance its logical clock to be past that logical time. So this will always be in the past for that server, so it can always answer it.
Oh, I see. Okay, thanks.
Alan Clement from MPI. Little curious about one of your claims for a goal was that it's an order of operations that makes sense to the user.
Yes.
And what you're replicating in the system is a set of write sets, effectively. Mm-hmm. Basically, the changes that a user is going to choose to make based off the state they observe. How is this final state of the system reflective of the an order of user operations that makes sense?
I'm not sure I understand the question. So the causal order, whatever order a client does operations in and whatever order they see state in, it'll enforce this in the subsequent ordering. So if I do something and I do something else, my second operation will show up before my first. But if I read some data from you and then I write something else, my write will show up after whatever I read that you wrote.
Yes, but if the order that the writes actually appear, if the decision I make for what I'm going to write back is influenced by the values that I read. Yeah. It's not just I read after, but I chose to do something based off of the values that I read. So the user operation, the user choice that was made isn't reflected anymore. This is now the order of writes that I made independent of the choice of what I wanted the system to do.
Well, so if a user wants multiple writes to show up together, or they want to ensure that some value shows up with the other value that they wrote, they should use a write-only transaction to ensure that these things are there. You have to use some sort of transaction to make these things appear atomically.
Okay, let's take this offline.
Okay.